Okay, so have you ever really looked at a massive bridge packed with cars and just wondered how? Or how the tiny little parts in your phone can take a beating day after day? Well, it all comes down to this constant, invisible battle between something called load and deflection. Today, we're going to pull back the curtain on the hidden science of how things bend without breaking.
It really all boils down to this one simple question. I mean, think about it for a second. You can bend a paperclip and it just stays in its new shape. A huge tree branch sways like crazy in the wind, but doesn't just snap in half. How is that possible? Why does one material give and flex while another one just shatters into a million pieces? That's the fundamental puzzle we're going to solve today.
All right, so to really get to the bottom of this, we've got to get on the same page with two super important concepts: load and deflection. You can almost think of it like a constant dance that's happening literally everywhere all the time. A force gets applied and a material has to respond. It is the fundamental challenge every single engineered thing faces, from the biggest building to the smallest microchip. So let's just break it down nice and simple. A load is just any outside force. It could be the weight of traffic on a highway, the wind pushing against a skyscraper, or even just your finger pressing a key on your keyboard. That's the load. And deflection, well, that's just the bend. It's the flex, the little bit of movement that happens because of that load. And honestly, the whole game of engineering is about managing that deflection, allowing for just enough bend while making absolutely sure it doesn't break.
And seriously, this isn't just about giant, impressive structures. It's happening right now, all around you. The very chair you might be sitting on, it's deflecting under your weight, even if you can't see it. The wings of an airplane? Oh yeah, they're designed to flex and bend way up there in the sky. Understanding this constant tug-of-war is the absolute key to how we build our entire world.
So how do we win this battle when we're talking about really, really big things? Well, for that, we turn to the true giants of the material world. These are the workhorses of construction, the materials that literally form the skeleton of our modern civilization. We're talking about the titans, right? You've got reinforced concrete and those classic steel I-beams that make our cities possible. You've got asphalt, which, believe it or not, is this incredibly complex mixture paving our way everywhere. And now, we're seeing all these amazing wood composites and fiber-reinforced polymers show up as lighter but unbelievably strong new players in the game.
Now, what's so cool about this is that each of these materials has its own unique superpower. So look at concrete. It's an absolute champion at resisting being squashed, a force we call compression. Steel, on the other hand, is incredible when you try to pull it apart. That's called tension. This also makes it ductile, meaning it can stretch and bend a lot before it even thinks about snapping. And knowing this difference? It's everything, because these materials almost never work alone. And this is where the real magic happens, in what we call composites. You take steel, which is amazing in tension, and you stick it inside concrete, which is a beast in compression. What do you get? Reinforced concrete. A super material that's way, way stronger than either of its parts could ever be on their own. It's the same idea with adding fiber mesh to asphalt. You're not just mixing things together, you're building a dream team.
But it's not all about giant buildings and bridges. Not even close. Now we're going to shrink things down and dive into the world of specialist materials. And these are materials engineered with just breathtaking precision for one very specific and often very extreme job. First up, let's go to the high-stakes world of high-performance machines, where every single gram, every millimeter can be the difference between success and failure.
I mean, check this out. We're talking about natural rubber that lets a drone's wing completely change its shape without a single mechanical hinge. Special rubber compounds filled with carbon black so a massive tractor tire can flex and bend over rough terrain without tearing apart. Paper-thin metal alloys that can spin at insane speeds inside a jet engine without failing. These aren't just materials, they're bona fide masterpieces of engineering.
And believe it or not, that exact same level of specialization is happening inside the human body. The challenge here is totally different, though. You have to make materials that can work with our biology, or in some cases even copy it perfectly.
Think about the arch wires and braces. They're often made of nickel titanium, which is this incredible memory metal that wants to return to its original shape, applying this constant, gentle force to move your teeth. Or the special gels inside blood collection tubes designed to separate samples perfectly without messing with the results. We're even designing materials to perfectly mimic the flex and strength of a human sternum for testing new medical devices. It's a world where precision is absolutely everything.
So where could this possibly go from here?
Well, it looks like the future is being built by looking in two completely opposite directions: the absolute genius of the natural world around us and the mind-blowing power of the incredibly infinitesimally small. So let me just throw this question at you. What if you didn't have to bolt a piece of metal to a piece of ceramic? What if you could create one single component that starts as one material and just seamlessly blends into the other, with no joint, no seam, and no weak spot?
This is the revolutionary idea behind something called functionally graded materials, or FGMs. Okay, so picture this. On one side, you've got 100% pure ceramic, which is amazing at handling crazy high temperatures. On the other side, you've got 100% metal, which gives you all the strength and flexibility you need. But in the middle, instead of a sharp line, you create this smooth, perfect gradient that blends their properties together. You're literally engineering the best of both worlds into one single piece. It's incredible.
And where do you think we got the inspiration for such a futuristic idea? You might be surprised. We found it in a scorpion. That's right. Researchers figured out that a scorpion's exoskeleton is a natural FGM made of layers with different stiffnesses that make it both unbelievably tough and really flexible.
This whole concept has a name. It's called biomimicry. You see, nature has been solving these load and deflection problems for millions and millions of years. So by studying its solutions, from a scorpion's armor to how a tree resists the wind, we get these amazing shortcuts to developing the next generation of materials. It's like having access to the best R&D lab in the universe.
And we are pushing these ideas all the way down to the atomic scale. We're weaving composites with things like carbon nanotubes to create materials with strength-to-weight ratios that are just off the charts. We're designing nanoribbons for the next wave of electronics and building these tiny graded beams for devices you can't even see. We are literally engineering our future one atom at a time.
So in the end, whether you're talking about a massive concrete beam holding up a highway or a futuristic nanocomposite inspired by an insect, it all comes back to that same fundamental dance: applying a load, managing the deflection, and engineering a material that has what it takes to bend without breaking.
Which leaves us with one last really fascinating question. The Stone Age was defined by stone, the Bronze Age by bronze, the Iron Age by iron. You could say we've lived through an age of steel and are now in an age of silicon and polymers. Looking at all this incredible innovation, you just have to wonder, what single material will be the one that defines our future?